All right, today we're going to pull back the curtain on one of the coolest magic tricks your computer performs, like every single second of the day. We're talking about memory management. Let's dive right in. So, have you ever actually looked at all the stuff you have running on your machine? You've got a game open, a web browser with like 100 tabs, Spotify, a video editor, and when you add it all up, it's way, way more memory than your computer physically has. How is that even possible? It feels like it's got to be breaking the laws of physics, right? Well, you're not wrong. In a way, it is doing the impossible. Your operating system, your OS, is basically a master illusionist. It creates this perception for every single application that it has a huge, wide open space of memory all to itself, when the reality is, it's a lot more cramped. So, okay, how does this grand illusion actually work? What's the secret? Well, it all comes down to the difference between what a program thinks it has and what it actually gets. See, the secret sauce is in these two types of addresses. You've got the logical address, which is the neat, tidy, continuous block of memory that your program believes it's working with, but then you've got the physical address, which is where the data is actually living on the physical RAM chips. And there's a special bit of hardware, the Memory Management Unit, or MMU, that's constantly working with the OS to translate between the two. So to pull this off, the first thing the OS does is it takes all of your physical RAM and just chops it up into these small, fixed-size blocks. You can think of them like empty parking spots in a giant parking garage. We call these frames. Then it does the exact same thing to your programs. It breaks them down into identically sized chunks called pages. So now we've got pages from our apps and frames in our memory, and they're all the same size. I think you can see where this is headed. And this right here is the brilliant part. The OS can take the pages from a single program and just slot them into any available frame, wherever it might be. They don't have to be next to each other at all. Just look at this diagram. Page 0 can go to frame 14, page 1 to frame 13. They're all over the place. The program itself is totally oblivious. It thinks it's all one big block, but the OS knows the real story. But, okay, this whole system creates a new kind of problem. What happens when a program needs to access a page that, well, isn't actually in physical memory at all? You see, the OS keeps this little scorecard for every single page. It's called a page table. And in that table, there's a super simple flag, a valid invalid bit. If the bit is V for valid, great, the page is in RAM ready to go. But if it's I for invalid, that means the page is currently sitting on your hard drive or SSD, not in the fast memory. So when your program asks for some data, and the MMU looks at that page table and sees that little I for invalid, it triggers an alarm. This is called a page fault. Now, it's not really an error in the traditional sense. It's more like a signal to the OS telling it, hey, I need you to step in here and go find this missing page for me. And when that happens, the OS has a very specific playbook. First, the hardware traps, which basically means it pauses the program and hands control over to the OS. The OS then checks, hey, was this program even supposed to be touching this memory? If it's all good, it finds an empty frame in RAM, goes and fetches the needed page from the slow disk, and swaps it into that empty spot. Finally, it updates the page table to mark that page as valid and tells the CPU, okay, you're good to go. Try that instruction again. This diagram gives us a great visual of that whole dance. You can see the request fails at step 1. The OS takes over, goes to the disk, which it calls the backing store, pulls the page into memory, fixes the table, and then restarts the instruction like nothing ever happened. Pretty slick. Now that whole process works perfectly as long as there's a free frame, but on a busy computer, memory is prime real estate. So what happens when there's no room at the in? This is really the million-dollar question in memory management. If a page fault happens and every single frame in your physical memory is already taken, how on earth do you make space for the new page you desperately need to load in? Well, we have to evict someone. The OS has to pick one of the pages that's currently in memory, we call it a victim page, and swap it out to the disk to make room. The whole challenge here is choosing the right victim. The best choice is a page that we won't need again for a while, because if we kick out something important, we're just going to have another page fault a millisecond later. It's all about performance. And as you might guess, this problem has led computer scientists to come up with a bunch of different strategies, or algorithms, for picking that victim page. They're really just competing ideas about how to best predict the future. So the simplest idea is FIFO, or first in, first out. It's literally just like a line at the grocery store. Whichever page has been sitting in memory the longest is the first one to get the boot when a new page needs to come in. It's super easy to code, but it has a huge flaw. It has no idea if that oldest page is actually really important and being used all the time. And this slide shows it perfectly. Just follow along. As each new page is requested, the one that's been there the longest, the one at the bottom, gets replaced. See how page 7 gets kicked out for 2? Then 0 gets kicked out to make room for 3, and on and on. It's simple, but maybe not so smart. Now, on the complete other end of the spectrum, you have the optimal algorithm. This is the holy grail. The idea is, look into the future, find the page that won't be used for the absolute longest period of time, and replace that one. This approach guarantees the fewest possible page faults. It's perfect. Of course, there's a catch, right? Unless your computer comes with a crystal ball, it can't actually predict the future. So the optimal algorithm is impossible to build in real life. We just use it in theory, as a benchmark, a perfect score that we can compare our real-world algorithms against. And that brings us to what's probably the most popular and practical approach, LRU, or least recently used. The logic here is just so elegant. It says, if a page hasn't been touched in a long time, it probably won't be needed again anytime soon. So instead of trying to predict the future, like the optimal algorithm, LRU just looks at the recent past, which turns out to be a really good approximation. And you can really see the difference here. LRU is keeping track of history. When it needs to make room, it looks for the page that's gone the longest without being accessed. It's a much more intelligent decision than FIFO because it's based on how the program is actually behaving. So let's just wrap this part up. This table lays it all out beautifully. You've got FIFO, simple and practical, but the performance is pretty bad. You've got optimal, best possible performance, but totally impractical. And then you have LRU, which really hits that sweet spot. It gives you good performance, and we can actually build it, even if it takes a little more work. You know, in the end, that's what this all comes down to. A balancing act. The entire magic show of modern memory management is this constant trade-off. We're always trying to find the perfect middle ground between the speed of our system, making the most of our limited memory, and the complexity of the code we write to manage it all. And that is the secret behind your computer's greatest illusion. So if you enjoyed this peek behind the curtain of virtual memory, do me a favor and hit that like button, share it with someone else who's curious, and definitely subscribe to Tech Talk 101 for more deep dives into the technology we use every single day. Thanks for watching.